Reflected light. So the thing about reflection that's really important to understand is that unless we are looking directly at a light source, the sun or a flashlight or a light bulb, what we're actually seeing is the light that's reflected off of the objects that we're looking at and coming into our eyes. Another thing that's important to understand is this law of reflection. And it makes sense if you think of it in terms of basketball. So if there's a person who's standing here, and he wants to pass the ball by bouncing it to the person who's here. There's an instinctive understanding that if people are very close together, the angle that the basketball has to bounce is very sharp as opposed to if they're very far apart. And you want to bounce it so that if you bounce it directly between them, then there's this understanding that the bounce coming in, the angle, is going to equal the bounce coming out. Now, in physics, we tend to think of things in terms of how it is related to the normal line. And the normal is always perpendicular to the surface. The reason why we do that is that it's often easier to figure out what the normal line is rather than what the nature of the surface is. So theta I means the angle to the normal, that's this, of the incident light. And incident means that it's incoming. And we show that because the arrow is going toward the surface. And then this is the reflected light, and this is the angle from the normal that reflected light has. And the law of reflection states that the angle of the incident light to the normal will be equal to the angle of the reflected light to the normal. This helps us make sense of the two different types of reflection that we have. We have specular reflection and we have diffuse reflection. Specular reflection comes off of a very smooth surface, like a mirror or a calm lake or glossy paper. It's very smooth, so the surface is almost completely planar. If I have all my incident rays coming in parallel, and if this is a very smooth surface, all of the normals will be parallel to one another. So that means that all the theta i's, the incident angles to the normal, all of these are going to be equal to one another. And if that's the case, all of the reflected light angles are going to be the same to the normal as well. And so the light that's coming in this way is going to bounce off cleanly this way. And if I look at it like this, parallel lights coming from a flashlight will shine off of the surface directly into the eye of the observer. There's no scattering of the light. The intensity of the light remains the same, and that beam of light is focused. And oftentimes we'll do this, like if people are trying to position their watch or something or a mirror so that the sunlight then shines a spot somewhere, have a cat chase that, go into the eye of somebody that you're trying to annoy. We understand that, and that only works with specular surfaces. I can't take a piece of cardboard and do the same thing. The reason why I can't do the same thing with cardboard is that I have what's called diffuse reflection. So this occurs in uneven surfaces, what we call matte. And these can be like regular paper, a non-glossy or polished surface, or it could be very craggy, right? It could be like the road, it could be sand. So the sand will give diffuse reflection at the ocean, whereas the ocean, especially if it's very calm, will give specular reflection. That's why we have the glare off of the ocean. We don't get the glare so much off of the sand. So if I have a close-up view of a matte surface, an uneven surface, here I'm kind of really emphasizing the fact that it's uneven. What happens is even if all of the incident light that's coming in is parallel to one another, right? So all of these purple lines are coming in parallel like a beam of light. Because the normal lines at the surface are not parallel to one another, none of these angles are the same to their normals, right? So even though they're coming in at the same angle to the surface, kind of, because it's craggy, this angle here is going to be much larger than this angle here. It's going to be different than this and this. And the more uneven the surface, the more you're going to have this incident light angle be completely different from one another. So as a result, my reflected light is being scattered in lots of different directions. So none of that comes back to the very few. So if I'm the observer right here, and I see this beam of light coming in here, only a little bit of the light comes back to me. Most of the light gets scattered away. So because the angles of the incident to their normals are not the same, all of the light gets scattered. It's in lower intensity and it's not focused. And we want that on a surface like this because we want the surface to reflect light so that we can see the paper. But we don't want it so that there's a glare on the light and I can't read the writing that's on the surface. So we often prefer matte surfaces when the surface is important to have something on it, like a painting or writing or the lines on the road, right? So we want the surface of our road to be matte so that we see the traffic lines very clearly. It becomes a problem if there is water on the road, like when there's snow melt, you get that really bad glare, all of a sudden you can't see any of the lines on the road. You don't know whose lane is what lane, you don't know where the edge of the road is, and that can be really dangerous. So there are times when we want specular reflection, and there are times where we want diffuse reflection, and we can control that by how smooth our surface is.